Hello everyone, welcome to this new tutorial on Quantum Espresso. Today I'm going to show you how to do simple calculations using Quantum Espresso. Basically, I will calculate three simple molecules. The first one is water, the second one is carbon dioxide, and the third one would be methane molecule. Remember that last time we had already installed Quantum Espresso here in QE 6.1, and if you remember that the main program is located in bin, which is this pw.x. So this program is responsible for calculating the electronic structure of the material. So I have already prepared some examples. You can see that here there are three input files: methane, carbon dioxide, and water. I will first start to run the calculations, and then I will explain what it is in the input file. So now we have the input file. How can we run the calculations? One way to do it is that we first pw.x and then redirect CH4. This is the input file, and then redirect the output to let's say .out. So this is usually the how it works, and since pw.x is not in the default program folder of this whole Linux system, so we need to specify where it is. So it is in not here. It is in home folder, QE tutorial, and see here, and QE 6.1 bin. Yeah. So now it is ready to be executed. Another thing that that is important is that if you run it this way, it will only run on one CPU, on one processor. If you have if your CPU have 4 cores, you need to use mpi run minus mp4, and then it can use all 4 cores. I will not use it here because sometimes this command gives some problems, and it is better to try to execute this command first, because this is the most basic one. And you just hit enter, and there's no output because the output is redirected to the output file. And what you can do is that so let's first clear it, is that you open a new terminal and use this command tail -f, that is to monitor the writing of this file, and you can see that these are the outputs. And we let it run, and I will explain to you what's in the input file. So we are running this one. So it has 4 name cards: control, system, electrons, and ions. in the control name card, you first has to specify the calculation is to relax the system. That is that you have the four atoms in some space, and it will automatically calculate the force on each atom and move according to the force, and then to reach a stable structure. So if you choose here relax, it will do multiple energy calculations. If you choose here SCF, that is like this, it will only calculate energy once. So this restart mode means that you don't restart from previous calculations, but from scratch. It means that it is starts from nothing. The prefix is the prefix of the output file, and the pseudo-dir is the directory where you put your pseudopotential files. So pseudopotential files are very important because this whole quantum espresso rely on pseudopotentials. Where can you get pseudopotentials? Pseudopotential, okay. If you Google pseudopotential quantum espresso, it will redirect you to this web page of the official website of Quantum Espresso, and you can find basically nearly the pseudopotentials for nearly all the elements in the elemental table. For example, if you would like to use calculate methane, you can download the pseudopotential for carbon here and for hydrogen here. I'll just click into it and see that there are actually many types of pseudopotentials. One thing to be noticed is that the first word before slash and after the first dot, that is PBE, for example here, PBE, PW, PW91. So the first word should be the same for each for every type of atoms in your molecule. Otherwise, it will conflict and you will it will show an error. For example, here we are calculating methane molecule, and they both use PBE functional. So this word means the functional is PBE, which originates from GGA, and for example here it means that the functional is PW, which originates from LDA. And these different pseudopotentials for different functionals cannot be mixed. So you download your pseudopotential to somewhere on your computer, and you specify the directory of the pseudopotential. And this out there specifies the where the program saves the wave function. Notice that usually this directory will be deleted. Should not will be deleted. If you don't delete it, it will not be deleted automatically. But you should delete it because it consumes very large space in your hard drive, and it is usually not used unless you would like to restart from a previous calculation. Then you should not delete it, but usually please delete it. In the second card, you can see that it's system, and yeah, so I noticed that the calculation has already terminated, so I will start and start the second calculation so that we can save time. Yeah, so the second calculation is for CO2. Oh no, CO2. Yeah. Okay, and of course we can monitor CO2.relax.out. Oh no, this is C02. CO2. Okay, to see that it is running. Let's come back to the input file. The iBroth is the is to specify the Bravais lattice. So the iBroth equals 1 means it is simple cubic Bravais lattice, and seldom 1 means that the lattice constant is 20 and the unit is Bohr. It is Bohr rather than angstrom. So if you would like to convert it here, like 1 Bohr is 0.5 angstrom. Okay, and net is means how many atoms are there in one unit cell. Here there are 5 atoms, and n-tip means how many type of atoms are there. So there are 2, carbon and hydrogen, and and E cut WFC means the cutoff energy for plane wave expansion, and usually the larger this value is, the let's say the more accurate the calculation will be. But usually when you increase this value, the calculation would be more and more expensive. So there will be some kind of balance. What people usually do is that they increase this value gradually to see that whether the total energy will saturate. And in this name card, it states what is the condition for the self-consistent calculations. So this is the mixing beta. It is between 0 and 1. Basically, it is a parameter that that you use when you do self-consistent calculation. You mix the newly generated wave function with the old wave function as the new input for the next iteration, and this mixing factor is 0.7, so which means that the new function generated, new wave function generated will be counted as 70%, and the old function will be 30%. So usually, if the system is not very complicated, you can choose like 0.7, 0.8. Like in our case, if the system is strongly correlated and it is very difficult to converge, you can lower it to 0.3, even 0.2, 0.1. Yeah. This convergence threshold is that when you do self-consistent calculations, like here, the estimated SCF accuracy will lower and lower until it reaches this threshold, and this round of iterations will be passed. So it is the condition that self-consistent calculation is reaches its end or not. And this name card is specific for the relaxed calculation. It basically means that the atoms can move, and the algorithm for moving the atoms around is BFGS. So it calculates the forces on each atom and move the atom according to the forces. Okay, so this calculation ended as well. So we now go to our third calculation, and that is the calculation of water molecule. Okay, and of course we would like to monitor the output file. And we come back to the input file. So the atomic species is where you specify the different elements. For example, carbon, and this is the mass of carbon is 12, around 12, and this is the pseudopotential file of carbon, and you need to specify every type of atom that you use with the name of the atom, the mass, and the name of the pseudopotential file, and the pseudopotential file should be located in this pseudo here. And then comes this atomic positions. Usually it is in unit alat, yeah, by default, which means that it is with respect to this cell dimension 1, that is the lattice constant. But now, for convenience, we choose angstrom, and we randomly place this these 5 atoms. So in this initial positions, it is far from the stable molecule. And the last thing that you need to specify is the K points. How many K points do you use for the calculations? Again, like the ECAT WFC, the more K points you have, the more accurate your calculation would be. But on the other hand, the more K points you have, the more expensive your calculation would be. That means that it will be much more slower. In our case, because we are only interested in single molecule, we just set it to 111. If this is a solid, and usually we use more than 111. For example, 222, that is very small, or 444, 20, 20, 20, yeah, something like that. And notice that quantum espresso is a plane wave expansion. Is a quantum mechanics calculation software based on plane wave expansion. So it assumes periodic boundary condition. So why we choose this simple cubic unit cell here is that you can see that this is 20 Bohr, that is around 10 angstrom, and you can see that the bonds of methane is much less than much shorter than 10 angstrom. So basically we are putting a small molecule inside a very big cubic box. Of course, the program will assume that this box will be periodic in 3D space, but since the molecules are only a small part of the space, so they will not interact with each other in different boxes. So we can calculate the property of a single molecule using this kind of software that assumes periodic boundary conditions. Okay, and let's take a look at CO2, the input file. Most of them are the same. Yeah, it's just that we choose different elements and specify different positions. And there are three atoms in one molecule and two types of atoms. In H2O, I change a little bit the E-cut WFC to 30 and the convergence threshold to more strict convergence, that is 1 minus 8, but it will not make so much a difference because we are this is just a simple calculation. These two are not important, we can delete it, just ignore it. Yeah, okay, so let's see what is the output file. You can see that there are many informations inside, but the important thing is this total energy, and then total energy again. So basically the program will do a self-consistent calculation and then calculate the total energy and then the forces on each atom and move according to the force a little bit to get new atomic positions, and then do the same thing again and again until the forces and energy difference is below a certain threshold. Yeah, that's here. This is the default one. We can change it to more strict conditions, but now we just keep it like that. And you can see this is the final coordinates here, and job done. Yeah, all the structures of the output files are the same. So it's again starting a self-consistent calculation, total energy here, forces, and new atomic positions, and then again and again until the forces and energy difference reaches this criteria. Yeah, and we would like to visualize it. First clear it, and we'll visualize it using X-Kristen. Okay, X-Kristen. Yeah. So for X-Kristen, it is an open source crystalline structure visualization software that you can find on Linux. You can Google X-Kristen and download it. It's quite simple to use. So we open it, file, open pwscf, that is the pw.x. You can open the input file or output file. I would like to open the output file, for example CH4, and display all coordinates as animation. Yeah? You can see that this is the initial, let's say, initial coordinates, and it's quite random, quite ugly. And as the calculation goes, it develops a tetragonal molecular structure. That is very much expected. Let's see that whether the angles and bond length is as in the literature. Okay, the angle is 109.529. So we see that methane molecule. Go to Wikipedia. You can see that this 109.5. This very accurate, and the bonding length between carbon and hydrogen would be 1.099 angstrom, which is 109.94 picometer. That is only a difference of 1.2 picometer. That is an error within 1%. So it is quite a good prediction. You should notice that I did not do the convergence with the ECAT WFC, nor the convergence with K points or etc. I just do this calculation, and it shows this close match. So again, we see the CO2, carbon dioxide molecule. This is before. This is the initial coordinates before relaxation. You can see that it is asymmetric, and the bond length is different. And the final coordinates is like this. Yeah, you can see that it becomes a line, and the distance between carbon and oxygen is 1.17. So let's see CO2 molecule. Just 116 picometer, that is 1.16 angstrom. So again, a small error of 1%. Now we look at water. Okay. The initial condition is like this, and after relaxation it goes to this shape. Let's see that the bond angle is 103.6 degree. And the real angle is 104 degrees. It's close. And for the distance, it is 97.89 picometers, and in literature it would be 95.84 picometers. So only two difference of 2 picometers. So now you can see that quantum espresso is quite powerful, and you can calculate simple molecules the bonding bond length, bonding angle, and structure of simple molecules. Yeah. So I would like to thank you for watching and see you next time.